Alright, so in this video I wanted to go over the concepts of concavity and how we can use concavity to do the second derivative test to help us find local extrema. Okay, so a quick little recap. So you remember how the first derivative told us if we're positive, if the first derivative was positive, the function was increasing. If the first derivative was negative, we said the function was decreasing. Well, the second derivative, instead, the second derivative tells us about concavity. So everywhere the second derivative is negative, we say that a function is concave down. So what does that look like? A concave down function looks like basically your upside down parabola. Everywhere the second derivative is positive, we say that the function is concave up. This is concave up. Right. And an inflection point is where concavity changes. So this occurs wherever the second derivative is either 0 or undefined. If this sounds kind of familiar, it's very much related to what we did for a critical value. And we said a critical value is where a first derivative is either 0 or undefined. Okay, here we go. For example, consider the following graph. Well, I'm going to draw a graph in a second. And I want us to determine where the function is concave up, where is it concave down, and list any inflection points. Okay, so let's see here. So consider this graph. Let's see if, oh my goodness, let's see if I can draw this graph here. Let's make it in red. Suppose our graph did something like this. Okay, and right here, this point right here, I'm going to call this x equals 1. Okay. So the question here is, for what values of x are we concave up and which values of x are we concave down? Well, let's just go in order from left to right. As we go in order from left to right along our horizontal axis, you notice that at first the graph appears to be concave down. All right. So the question becomes, for what values of x are we concave down? Well, we are concave down from, remember, x values. From x values approaching negative infinity until we get close to an x value of 1. So to be clear here, this is a graph of f of x, and f of x is concave down from negative infinity to 1. And then we start to switch our concavity. Now we go from concave down to concave up. Once again, the questions are, what values of x are we concave up? Once again, x values. We are going to be concave up from 1 to positive infinity. Because our concavity switched, meaning we went from concave down to concave up, or we could do it vice versa. Because the concavity switched, that means that we have an inflection point located at x equals 1. Because we went from concave down to concave up. So an inflection point is where your concavity switches. Okay, let's go on to the next example here. For the next example, I'm going to draw a graph of f prime of x. So keep in mind, before we did the original f of x, now I'm going to draw a graph of the first derivative. And once again, from this graph, we want to determine where the function is concave up, where is it concave down, and any inflection points. So for this graph, let's say it looks like this. Let's do this in blue. Let's make it do, well, that's freaky. All right, let's say the graph did something like this. Okay. And right here, this point right here, I'm going to call this x equals 5. All right, keep in mind, very important, what I just drew was the graph of f prime of x. This is not the original f of x, this is the first derivative. Okay, same question, for what values of x are we concave up? Okay, because this is not the original f of x graph, you just can't see, oh, this first part of the graph is concave up, and then it switches to concave down. No, this is the first derivative graph. So now instead, and this is what the hint is telling you, whenever we talk about the second derivative, we're talking about the derivative of the first derivative. So another way to look at to determine concavity is that your f of x is concave up wherever your first derivative is increasing. Because that means if it's the derivative of the derivative, that means the second derivative is positive. So one more time, you're concave up wherever your first derivative is increasing, and you're concave down wherever your first derivative is decreasing. Okay, so let's come over here. So let's start off with concave. Let's do concave down first. I chose that because if you look at the first part of this graph here, the first part of our graph, this first derivative is decreasing. For what values of x are we decreasing? We are decreasing from negative infinity until we get close to an x value of 0. Because the first derivative is decreasing there, we could effectively say that the function is concave down. The original function is concave down over those same x values. Then after x equals 0, we see that our derivative begins to increase. So that means that we are concave up for x values between 0 and 5. Okay. And then after we hit that peak of 5 in our first derivative, we see that we start to decrease again, and we see that we are decreasing for x values from 5 to positive infinity. Why positive infinity? Because we're talking about x values. That graph is going infinitely to the right. That's what this arrow means, right? Down and to the right forever. Keyword is to the right. Okay, so once again, the key here is that this was a graph of the first derivative and not the original function. And inflection points. Inflection points are going to be where your second derivative equals 0. Okay, where you bottom out, or maybe top out. In this case, we see that we're going to have two potential inflection points. One right here at x equals 0. We're also going to have one right here at x equals 5. So two, I'm going to write possible inflection points. I mean, they actually are inflection points, but... So the possible inflection points include x equals 0 and x equals 5. Why is that? Because that is where the second derivative is 0. Okay, if you remember when we started to talk about the first derivative test, we said that where the function flattens out, that's where the derivative is equal to 0. Well, here, because it's the graph of the first derivative, that means that the second derivative is equal to 0 there. Okay, hopefully that wasn't super confusing. All right, keeping it moving. Here we go. Another type of question you may come across in the homework is this. Consider the following function. Determine the concavity at x equals 1 and also find any inflection points. Okay, so let's handle the first part. Determine the concavity at x equals 1. Well, to determine the concavity, we need to first find the second derivative. Before we can find the second derivative, we need the first derivative. So here we go. F prime of x equals... let's see here, you should get a 24x squared plus 6x minus 6. I'm going to do f double prime, which is just another derivative. I got 48x plus 6. Okay. To determine the concavity at x equals 1, just simply plug in x equals 1 into your second derivative. So that's 48 times 1 plus 6. We get, if my math is correct, you should get 54. Key here is that it's positive. So if the second derivative is positive at an x value, that means that we are concave up. Okay, so we can say that the function is concave up at x equals 1 because we got a positive second derivative there. Okay, inflection points. To find the inflection point, we need to determine where the second derivative is either 0 or undefined. Well, our second derivative is 48x plus 6, so it's going to be defined everywhere. I mean, if you look at the domain of that second derivative, it's all real numbers, so it's defined everywhere. However, we can set that equal to 0. So the inflection point will be where 48x plus 6 equals 0. Solving for x, I'll save you the steps. You get x is a negative 6/48, which reduces to a negative 1/8. Okay. Now, this is an inflection point candidate. This is a possible inflection point. Meaning if there is an inflection point, that's the only option. It can only be x equals to negative 1/8. To determine if we have an actual inflection point there, we have to check to see if the concavity changed to the left and to the right of that x value of a negative 1/8. So to do that is we can do f double prime of negative 1. Okay, so this is going to be an x value to the left of that negative 1/8. And then we're going to do f double prime of 0, and this will give us the concavity to the right of that x value of a negative 1/8. So f double prime of a negative 1 is 48 times a negative 1 plus 6. Just plugging into the second derivative. You get a negative 48 plus 6, you should get a negative 42, which indicates the function is concave down to the left of our inflection point, potential inflection point. F double prime of 0 will give us 48 times 0 plus 6 gives us a positive 6, keyword positive. So we are concave up to the right of that inflection point, possible inflection point. Therefore, since concavity changes, we can conclude that x equals a negative 1/8 is an inflection point. And I apologize for my handwriting. Okay, so the key there is once you figure out your potential inflection point, make sure you check on both sides of it and make sure that concavity actually changes. There's no guarantee that that will be the case. All right, wrapping up this video, I want to get into the second derivative test for local extrema. So to recap, we know that local extrema can only occur at critical values. So previously in class, we used the first derivative test to determine these local extrema. Well, it turns out that you can also use the second derivative test to determine, oh my goodness, is another way of determining local extrema. Okay, so if C is a critical value, then if f double prime of C is negative, then x equals C is a local max. Well, why is that the case? It's based off of concavity. If we are concave down, which the f double prime of C negative indicates, and C is a critical value, that means that we have a relative max or a local max at x equals C. If instead f double prime of C gives us a positive value, that means that we are concave up at x equals C, which indicates we have a local min at x equals C. And so a potential drawback though of this test is that if f double prime of C equals 0, then you have to go back to the first derivative test. We say the test is inconclusive. So because of that, because we have the potential to get an inconclusive test, what I recommend, and since you guys are already familiar and comfortable with it, just do the first derivative test if you're trying to find your local extrema. Just do your first derivative test. Okay, for example, find the local extrema of the given function. So the first thing we have to do is find critical values, which involves finding the x values for which the first derivative is either 0 or undefined. So first step, find the first derivative. So f prime of x should be 9x8 x to the 8th power minus 21x to the 6th. Okay, and the derivative 2 is constant. Okay. And now we are going to set that equal to 0 because it's defined everywhere. So 9x to the 8th minus 21x to the 6th is equal to 0. We need to solve this for for x. So first thing we could do is pull out a GCF. What's in common? We have a 3 in common. We have an x to the 6th in common. So that should leave us with, let's see here, a 3x squared minus 7. Set that equal to 0. And we're going to set up now two different equations, right? We have to take 3x to the 6th, set that equal to 0. And also we have to solve 3x squared minus 7 equal to 0. Okay. Well, the first equation, if you divide through by 3, you get that x to the 6th is equal to 0. You take the 6th root, I know it sounds weird, but you take the 6th root of both sides, and you just get that x is equal to 0. So that's a critical value, x equals 0. The other critical value can be found by adding the 7 to both sides, so 3x squared is equal to 7. Dividing through by 3. X squared is equal to 7/3. And now take square roots of both sides, but don't forget, very important, when you take the square root of that right side, don't forget both the positive and negative root. Okay, so taking square roots of both sides, we get that x is equal to both positive and negative square roots of 7/3. Do not forget the plus or minus. So we have a total of 3 different critical values. Total 3 different critical values. Now, as I said, the instructions may say use the second derivative test, but like I said, we're just going to go ahead and use the first derivative test here. Okay. So to do that, we're going to have a number line, a colorful one at that, and then we're going to have place our critical values on this number line. We're going to have negative square roots of 7/3. We're going to have 0. We're going to have positive square roots of 7/3. Okay. Now what we're going to do is we're going to grab a representative from each of these regions and determine the sign of the first derivative. Remember, I'm using the first derivative test here. So for instance, I need to find f prime of, well, let's do this. Let's figure out what the square root of 7/3 is so we can get a decent approximation here. So let me switch over to my calculator. So let's see here. The square root of 7/3 is 1.5, okay? So a -2 should do the trick for this left region. Let's go back. F prime of -2 should be a x value that's to the left of a negative square root of 7/3. Okay? I'll plug that into a second. Let's go ahead and get all the representatives. So in between a -7 square root of 7/3 and 0, we can use, because remember, square root of 7/3 is 1.5 and some change. So let's do f prime of -1, f prime of 1, and we can do f prime of a +2. So those will be our representatives. Okay, so now I am going to use my calculator to evaluate these values in our first derivative. So let's see, our first derivative was 9x8 minus 21x6. So let's go to our calculator. All right, so let me just double check, make sure my calculator is set up. Hit second table set. Okay, move my independent variable over to ask. Okay. So here we go. Now we go to y equals. Clear whatever else is in there. 9x to the 8th minus 21x6. Okay, there's our derivative. So now we're going to go to our table, second graph. And we're going to do -2 was our value in that left region. We get a positive value. Then I believe we did -1. Oh, delete that. Sorry, didn't see that. Uh-oh. It's easier if I do this. Let's see here. -1. Okay. Gives us a negative value. And then we did, what did we do? We did +1. And then we do +2. I believe those were our values. Let me double check. -2, -1, +1, +2. All right. So for -2, we ended up with a positive value. So I believe this was assigned positive, then negative. And then for 1, we got a -12. So we were negative, and then we were positive at 960. Okay, so that is the signs of our first derivative over those intervals. Now, here we go. So now we're going to do what we did first derivative test, okay? Go to your negative square roots of 7/3. Okay, because it's the first derivative test, that means that to the left of a negative square root of 7/3, our function is increasing. Critical value, we flatten out. And then to the right, we begin to decrease. So that means that we have a relative max at x equals negative square roots of 7/3, or a local max. Excuse me. Okay. Now, if you look at 0, if you remember in class I told you guys, don't always fall in love with these signs alternating. If you look at 0, both to the left and the right of 0, we see that the function is decreasing. What that indicates is that there is no local minima, or excuse me, no local extrema at x equals 0. So x equals 0, even though it's a critical value, it is not a local min or max. Now, going over to the positive square roots of 7/3, we see that to the left of this square root of 7/3, we are decreasing. And then to the right, we begin to increase. Therefore, we're going to have a local min at x equals positive square roots of 7/3. So what this basically means, y'all, if we were to go back into the second derivative test, what we would find is that, I'm not going to do it, but if you were to go back and calculate f double prime and evaluate the negative square roots of 7/3, you would end up with something, let's see here, something negative, because we have a local max there. If you ended up taking your positive square root of 7/3 and plugging that into the second derivative that I didn't calculate, you would end up with something positive because your concave up there, and then x equals c, which is the square root of 7/3, would be a local min there. However, and this is why I recommend just do the first derivative test, it turns out that f double prime of 0 equals 0. So the test was inconclusive, and we had to come back to the first derivative test anyways. So one more time, my recommendation is, if you get to a question like this, just do the first derivative test. All right, hope this video helped you guys out, and I'll see you in the next one.